Hi, I'm Amir Hossein Mirza Bozorg, and in this video I want to talk about laser shock peening using subroutines in Abaqus Part 1. How to ask your video related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We try to answer all questions regarding the video details in the comments below. This is the table of content. I will talk about Abaqus steps for LSP simulation, reference papers, single and multiple shot simulations, material definition, loading definition, single shot modeling procedure, subroutines for single shot analysis, coarse and fine mesh definition, comparing the results of the fine and coarse meshes using the PEQ, multiple shots modeling procedure, multiple shots pattern, comparing the simulation result and the requested pattern, comparing the results of the single and multiple shots, and finally, next tutorial content. In this tutorial, the use of DLOAD and VDLOAD subroutines for defining the laser pressure in the laser shock peening process is explained according to two papers. The pressure induced by laser shot is not uniformly distributed and has a complex function depending on both time and position. To define such complex function, DLOAD or VDLOAD subroutines must be used according to the defined step in the Abaqus steps module. In this tutorial, both the single and multiple shot simulations are discussed in detail. Now I want to talk about Abaqus steps for LSP simulation. If we want to use the Abaqus standard solver, we must select the dynamic implicit step and we must write the DLOAD subroutine. And if we want to use the Abaqus explicit solver, we must select the dynamic explicit step and we must write the VDLOAD subroutine. Now I want to talk about the reference papers. The laser shock peening process is simulated according to these papers. These articles use DLOAD or VDLOAD subroutines to define the complex laser pressure distribution as a function of time and position. There are several parameters for the multiple shot simulation, including position of the starting shot, which is the coordinates of the center of the first shot, a scanning path. Actually, the laser traveling direction can be the same or change in the every other line. For example, in this simulation, the laser traveling direction is changing in every other line. The other parameters are the values of delta y and delta x. Delta y is the distance between the center of two shots in the y direction, and delta x is the distance between the center of two shots in the x direction. And finally, the number of shots in x and y directions. Now I want to talk about defining silent boundaries. Here we have a LSP simulation, and here we apply the laser shot. Actually, by applying the laser shot, propagating mechanical waves will be produced in the specimen. And to avoid the reflection of these propagating waves, we must define silent boundaries around the specimen. And to define the silent boundaries, we will use the infinite elements. Here we have defined infinite elements around the finite elements. When the propagating mechanical waves are produced here and they reach to the silent boundaries, they will not be reflected and all of them will be absorbed in the silent boundaries. And there must be enough distance between the laser shot region and the infinite elements. If the distance is not enough, the result will be inaccurate. Now I want to talk about single and multiple shots simulations. To do the single shot simulation, we have used both of the coarse mesh and fine mesh. And the single shot simulations show that the result of the coarse mesh is entirely inaccurate. So the multiple shot simulation has been only conducted via fine mesh. This is the single shot specimen's geometry from the XY view. Actually, the specimen consists of 6 regions. The central region is meshed using the finite elements, and there are 5 regions around the main region acting as the silent boundaries, and they will be meshed using the infinite elements. And this is the 5th region. And this is the single shot specimen's geometry from the XZ view. The material definition includes the definition of density, elastic properties, and plastic properties. And the plastic behavior is defined using the Johnson-Cook model. Now I want to talk about the loading definition. By inducing the laser pressure is applied to the model. It is a function of position and time, and we can assume that it is equal to the multiplication of a function depending on time and another function depending on position. And here we have the function depending on position. Actually, R0 is the radius of the laser spot, and R is the distance between the center of the laser shot and every other point on the surface. If we name the function depending on time as Pt, it has such behavior, and we can approximate it to this behavior. The approximate behavior of Pt consists of 3 parts. In the first part, it is increasing linearly, and in the second part, it is decreasing linearly, and in the third part, it is equal to 0. And here we have the mathematical descriptions of 3 parts. And here we have the values of the input parameters of the loading definition. From the value of spot size, we can calculate the value of R0, and here we have the value of Pmax, and here we have the value of Td. Actually, 10 nanoseconds is required for the pulse to reach Pmax, and it takes an equivalent duration to drop to 0. Now I want to talk about single-shot modeling procedure. All of the single-shot simulations have been conducted via dynamic implicit step. Hence, the laser pressure has been defined via the DLOAD subroutine. Additionally, the VDLOAD subroutine will be illustrated for use with dynamic explicit step. Now I want to show you the DLOAD and VDLOAD subroutines for the single-shot simulation. This is the DLOAD subroutine for the single-shot simulations. And first, I have defined the input parameters, and as you can see, this code is written in a parametric form. So, by changing the value of these parameters, you can do a new simulation. As the PT includes 3 parts, I have written 3 if statements corresponding to each of the parts. And then I have defined PR, and the total pressure is equal to the multiplication of PT and PR. And this is the VDLOAD subroutine for the single shot simulation, and as you can see, I have defined different values for input parameters. And the logic of the VDLOAD and DLOAD subroutines are the same, and they are similar to each other. Also here, I have written 3 if statements. Now I want to talk about step module settings. I have defined one dynamic implicit step, and here I have assumed that the total value of time period is equal to 12 TD, which is equal to 2 TD plus 10 TD. In this duration, the laser pressure is more than 0, and in this duration, the laser pressure is equal to 0. And here, we must input the real time of the process. And as the simulation is highly dynamic, the application is set to transient fidelity. Now I want to talk about the incrementation settings. To capture the wave propagation phenomenon during the process, a small time increment size should be used. So I have set the values of initial and maximum time increment size to 10% of TD. Here I have defined the laser pressure by defining pressure, and I have set the distribution to user defined, and Abaqus has mentioned that user subroutine DLOAD must be attached to the analysis job. Now I want to talk about the mesh definition. For the coarse mesh, I have set the approximate global size of the elements to 0.3, and here I have just leave other parameters as default. For the coarse mesh, also the mesh is uniform through the thickness and no bias is used. And for the fine mesh, I have set the approximate global size of the elements to 0.15. And I have used bias through the thickness direction, and the element size is changed from 0.3 at the bottom of the specimen to 0.15 at the top of the specimen. Now I want to show you the CAE model of the single shot simulation. In model 1, coarse mesh is defined, and in model 2, fine mesh is defined. And this is the specimen or workpiece. Here we have the material definition. In the TI elastic, only the density and elastic properties are defined, and it will be assigned to the silent boundaries. And in the TI full, all of the density and elastic properties and plastic properties are defined, and it is assigned to the main region. Actually, we have defined the Johnson-Cook hardening with rate dependency and without temperature dependency, because we want to do a highly dynamic simulation without thermal dependency. And if I change the coloring rule, you can see that the different materials are assigned. In the assembly module, we must put the specimen in the correct position relative to the global coordinate system, because the subroutine uses the coordinates according to the global coordinate system, so the position of the specimen must be correct. In all of my simulations for this tutorial, I have put the global coordinate system at the corner of the specimen. And here we have the step settings. As there was no need for the history outputs, I deleted it. And this is the field output settings. There is no setting in the interaction module. In the load module, I have defined the laser pressure, and no boundary condition is defined because we have defined silent boundaries around the main part of the workpiece, and also no initial condition is defined. And here we have the coarse mesh, and as I want to compare the coarse and fine meshes simultaneously, I create another viewport. This is the coarse mesh and this is the fine mesh. Now I want to compare the results of the fine and coarse meshes using the PEQ. Here we have the coarse mesh results, and here we have the fine mesh results. To better demonstrate the effects of the mesh size on the outputs, PEQ is visualized and compared here between the two cases. As you can see here, the PEQ contour is not reasonable at all, so it is not accurate. But here it is reasonable, so it is more accurate. Now I want to go back to Abaqus to show you the results of the fine mesh. First, I increase the number of colors in the legend. I want to check the contour of PEQ. Now I go back to the slides. Now I want to talk about multiple shots modeling procedure. The multiple shot simulation has been conducted via dynamic implicit step. Hence, the laser pressure has been defined via the DLOAD subroutine. Additionally, the VDLOAD subroutine will be illustrated for use with dynamic explicit step. Now I want to show you the DLOAD and VDLOAD subroutines. Here we have the DLOAD subroutine for multiple shots, and also I have written this code in a parametric form. And by changing these parameters, we can define a new pattern of laser shot process. And also n is the number of shots in the x direction and m is the number of shots in the y direction. And this is the VDLOAD subroutine for the multiple shots. And as you can see, this code is written for a LSP process with different laser specifications. And by changing the parameters of the code, a new pattern of shots will be produced. Here we have the multiple shots specimens geometry from the XY view. And here we have it from the XZ view. And in this simulation, we want to create this pattern of shots. We have 2 shots in the x direction and we have 3 shots in the y direction. So the total number of shots will be 6. And here I have assumed that the delta x and delta y are equal. About the step module settings, I have defined a dynamic implicit step and I have assumed that the total value of time period is equal to 72 TD, which is equal to 6 multiplied by 12 TD. And 6 is the total number of shots and 12 TD is equal to the duration of each shot. And also I have used the same settings for the incrementation tab. Here we have the multiple shot simulation results. And as you can see, the PEQ contours are different between 2 columns. As a result of the interaction between the shots and their effects on each other, there is an apparent difference between the PEQ for the 2 columns. In fact, the superposition of the mechanical waves in the material is the cause of this difference. In the case of a longer period and distance between the shots, there would be fewer deviations between the contours of the 2 columns. Here I want to compare the simulation result and the requested pattern. Here we have the requested pattern and here is the result of the simulation. And as you can see, they are similar to each other. And here we have the multiple shot simulation versus single shot simulation. Now I want to show you the results of the multiple shot simulation in the visualization module. Here we have the multiple shot simulation results. I increase the number of colors. Now we are checking the von Mises stress contour. Here we have the first shot, and the second shot happens, and then the third shot happens, and then the fourth shot happens, and then the fifth shot happens, and finally the sixth shot happens. Now I want to check the PQ contour. First shot, second shot, third shot, fourth shot, fifth shot, and sixth shot. And as you can see, we have 2 shots in the X direction and 3 shots in the Y direction. The package, including Abaqus files, is ready to purchase. The package price and payment details are provided in the video description. In the following tutorials, I will talk about other features of LSP process simulation, specifically for multiple shots. You can contact me using Telegram or WhatsApp, or you can send email to me. We can have one-on-one tutoring on the AnyDesk, WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects, and we offer support in writing the modeling and result discussion parts of your thesis. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.